Yeah, can someone confirm that you can hear me, please? Unmute and
Yes, sir.
thank you. Thank you. Okay, I didn't know. Okay, thank you very much for this invitation. And yeah, so I'll speak today about puzzle and the central concept in mathematics and actually also computing. And maybe and another example of that. Okay, so the puzzle is this thing called the Tower of Hanoi. Let me show this in the camera. This is a physical one. Many of you may have seen this. Many of you may know how to solve it, but you also see it on the screen. You're all old enough to do this. I mean, I got this physical one for my daughter when she was, I tracked in third standard. So and I had to tell her the general basic method, but she could solve it then. It took time, of course, for a 10 tower. But we can also, now this one is maybe a bit too symmetric to fully illustrate what we want to do. I'll tell you what I want to do, of course, by and by. But so we'll take a variation of this. Computer here program can also solve the random tower. Okay. So I would, of course, encourage you, if you don't have this, to get a physical one. If you don't have a physical one, I just checked yesterday. There are Android apps with which you can play. You can also do it here, but this is clunky. This is homemade. I made the version above that is up to the thing with manual moves for another talk, and this manual move part for this talk. Okay. So anyway, a random tower will illustrate what is the issue with this Tower of Hanoi. So the Tower of Hanoi, there are 3 pegs. Initially, everything is on one of them. So I'm in this illustration. By the way, this is online in the public web. So you can go and play with it, or maybe in the chat or something. I will share the link later. So this is, where was I? Yeah. So there are 3 pegs, and here they're all 3 non-empty with a random tower, and coins are on these pegs. And you will notice that one constraint here, so some big ones are here, some small ones are here, but the one constraint is that the bigger peg is always below the smaller one. Okay, so you can never put a bigger coin is always below a smaller coin. So this is what a Tower of Hanoi is. It is it's a puzzle where you have the following constraint, where you're supposed to make moves. Let's go back to maybe a smaller thing. Let's take a smaller point, and I will just show you what I mean by solving this. Let's reset. So here is a 3 tower. I am supposed to make moves which will transfer this to the left peg. And I'm always supposed to do it in such a way that the smaller peg is always below the larger peg. Okay. So I'm sorry, smaller peg is always above a larger peg. So for instance, this I could move here, and then let me move the middle right. Now at this point, I cannot move the right to the left. You see, a legal move doesn't include that because that will put this on top of this. However, I can move the left to the right. I can move the right to the left. Oh, so that was a wasted move. I clicked the wrong one. I meant this one. And then maybe right to the middle. And then let's send this guy here. Middle to, no, that's the right one, to left. As you see, this is such a clunky interface. I'm clicking the wrong things, but this is homemade. So, and finally the left one, so it's the left one that goes, sorry, the right one. This one is in the middle. I can't tell here, middle to the left. Okay, so this was the success. So this was an example. Of course, let's watch a computer solve this. Okay, so let the computer solve it in the background while I say something about this. So I hope this problem is clear. We have this tower and we are supposed to move coins. I can move this here, I can move this here, but I cannot move the bigger coin on top of the smaller coin. Okay, and I'm supposed to solve this. Oh, it solved it already. You'll notice it took rather a large number of moves there. It took 1032, but that was because it's counting from earlier. This is, by the way, not its actual speed. It solves quite a bit faster than this. The animation has been slowed down. I will go through the example of this and solve it. Okay, so, okay, 1023 is actually the optimal solution. There were the 11 moves. It didn't reset the counter when I moved things around. but this was the optimal move. Okay, so let's get to this issue. So the problem we are trying to address is we have maybe a random tower and we want to solve the tower of Hanoi. And I want to teach a computer how to solve it. I want to have a procedure. Okay. I've taken the random tower as a variation. It was actually counting moves was a colleague's suggestion. Actually, a random tower is easier than the standard one, but the standard one being very symmetric, you can write down some sort of special procedures for that without addressing the general way. And my goal is to understand the general way. So what is the general way here? How do we solve the tower of Hanoi? So there's a central principle that I want to illustrate, which as you were in the TEDx talks, you saw fractals. This is somewhat related to that, but it's more concrete and actually much more widespread, which is the idea of recursion. Okay, so the idea of recursion is, well, first of all, before talking about recursion, when you want to solve a problem, the general method here is to break it up into smaller problems. And in such a way that if you can solve each of the smaller problems, then you can solve the original one. What do you do with the smaller problems? Break them up into even smaller ones. Go all the way down to tiny ones. And when you go all the way down to tiny ones, you would be able to solve it in some special way. And you have to be able to put together the solution. Okay. This you can call sort of modularity, like a modular kitchen or whatever it is. And this holds not just for solving problems. It's also something that you would talk about in languages. Sentences are formed by putting together phrases, but in foundations of mathematics and many other cases in the design, in the computers we are all using now, where small components give bigger components and so on. But recursion is a particularly nice form of modularity where you break the problem into similar problems. So solving a problem involves solving similar problems, but with smaller parameters. Okay. So strictly you would call it primitive recursion if it's smaller. If you allow it to sometimes get larger and sometimes smaller, then that's general recursion, which may or may not stop. Maybe you did it wrong, but let's focus. Let's just think that we have a problem and we solve it by solving simpler problems. Okay, that is the idea. Okay, so let's get through this. Let me just start. Okay, I'll let's take something small. Let's say 4, and reset this. And now I'm going to put the speed back. Let me just, that was not. Let me just put it to its default speed, which was tuned as being reasonable. And I want to illustrate what I mean by this, by solving this. Okay, so so by the way, though this is called Tower of Hanoi, it has many other names, and we'll come to that in a moment. Let us watch what the computer is doing, not in detail, but one crucial point here at which I'm going to stop it. What did it do here? We want to move the lowest coin. So how do we move the lowest coin? Before we move the lowest coin, we have to get rid of everything above it, because you're only allowed to move the top coin. Okay. And we want to move that lowest coin to the left. So let's get rid of all these to the right. But what is that? That is another Tower of Hanoi problem. But it's a Tower of Hanoi problem with 3 coins instead of 2. Okay. So our first step is we'll solve a smaller Tower of Hanoi problem, one with 3 coins. Okay. Our second step is just send this here, one move here. And now what do I have to do? I have a 3 tower here and I have to move it here. That's again a smaller Tower of Hanoi. Okay, let's watch how we solve this. We have to solve the 3 one, so I have to send this lowest one here. So to do that, I have to solve a 2 tower. So let's solve the 2 tower. So I've solved the 2 tower here. Now this coin is free to go here. It starts. It's gone there. And now I solve a 2 tower again. Okay, so I have reduced solving a 4 tower to solving a 3 tower, solving a 3 tower to solving a 2 tower. And how do we solve the 2 tower? I have to move this coin here. Okay, so I have to get this out of the way. So I solve the 1 tower, which is simply move this here and stop. Okay. And then let us start again and watch. Now we can just move this here and then we solve the one time. So this is actually how the program is written. It goes all the way down. It has a tower. Okay. And it starts with this. So this is a single principle which is at the center of lots of solutions, both of puzzles like this and real problems. Okay. So well, let's look at the random tower and then we'll turn to another issue, which is how many moves this takes. Okay, so let's try to think about that a bit. And so but first of all, let's take a random tower. Ah, this one very nicely illustrated the point. Now, what if you want to solve a random tower? Remember, we want to put things in the last peg. Okay, so let's solve this manually. Okay, or maybe I'll get the computer to solve it. Let's see. We want to solve this 4 tower. Okay, now the largest peg is already here. So forget about it. That is solved. So we just have to solve a random 3 tower. Random 3 tower takes some work because this guy is in the wrong place. I have to move it here. Okay. For that, I will have to solve a 2 tower. And the 2 tower will be putting these two here on the right so that this guy is free to move here. So there are 2 obstacles to moving this here. This guy is in the way and this guy is also in the way. Okay, so one is in the way in the source and the other is in the way of the destination. So I want to get everything smaller than the third coin out of the way, which means I have to solve a 2 tower, a random 2 tower, and solve in the sense of putting things on the right peg. Okay, and how do I put this on the right peg? Well, this guy is free. So there is, and this peg is also free. So there is nothing that I need to do. So I simply start, I can just do it manually. I put it left to right, and then I put the middle coin to the right. Now this guy can go here. So this is the middle coin goes left. Okay, now I have to solve a 2 tower and that I'll send the right to the middle and then I will send the right to the left. And then finally I send the middle to the left and I have my success. Okay. So this is the simple principle that I wanted to see. We will see other examples of this. Okay. And so by the way, this took 6 moves. And if you may notice, or if you don't notice, we will do it again. If you did it for the other tower, it will actually take 7 moves. The best way of solving this takes 7 moves. So around, oh, sorry, it's 15 moves. For a 3 tower, it takes 7 moves. So it took 15 moves. So actually random towers are better, but for a human, they're harder because a human has to keep track of them. We are solving this, so we are solving that, etc., etc. And this can get a bit complicated. Okay, mentally. That is really the main skill once you understand the key idea of solving this. And I should tell you, if you try to 4 tower and so on is easy, but try to do a 10 tower. It's quite non-trivial, but you're all old enough, as I said. Okay, so far so good. We have discussed one example. Okay, and let's look at one more point. So how many moves did it take? And we'll try to understand this. Okay, so you can see the number here, 15. Let's take a 10 tower. 10 tower is the default. I'll put it at full speed and let's start. Okay, so it's going to take certain number of moves. You can all mentally, probably not all, maybe the more junior people here may not yet have the background, but you can mentally think this background is 1023. What do you think 11 tower will take? Okay, so since we are not interactive and the questions will come later, let me as well say it. So the random tower will take 2047 moves. No, sorry, 1024. Did it not reset? Hang on. I didn't reset the counter. I just changed it to 11. That's why I was getting the wrong count. The solution is perfectly fine. Okay. So the moves it'll take instead of 1023 will be 2047. And what are these numbers? What are these numbers? Many of you will recognize these are powers of 2 minus 1. Okay. So 15 is, so you take one tower will take 1, no problem. 2 towers will take 3. Okay, that's just add 1 to that. So number of moves plus 1 is going to be 2, 4, 8, 16, 32. It keeps doubling. Okay. Why does it keep doubling? It keeps doubling because every time we have, when we are solving a tower with 10 coins, we are solving a 9 tower, then making one move, and then solving a 9 tower again. Okay. So this means that your number of moves is doubling, and then we add 1. So if you are 1, then you double that, you get 3 and add 1. Okay. And so when you double 1, so when you double 3, you'll get, so you double 3, you get 6 and you add 1. Okay. And so you're always getting these things. And let me, for the more experienced of you, just quickly write down the formula and see. Oh, I made a mistake here. My setup is not good for writing. Sorry, this side screen, it's always going to be 2 to the n minus 1. My dual screen has not been configured correctly for writing, so you'll see very wide, but I think it's readable. Because, okay, so if those who know, if n is the number of coins, that is because by induction, so you do the same thing. So if I look at twice 2 to the n minus 1 and then 1. So I solve 2 towers of length n when I'm solving a tower of length n minus 1. Okay. Then I'll get this 2 times 2 to the n minus 1. And then I add 1 to that. That's going to be 2 to the n plus 1 minus 2 plus 1, which is going to be 2 to the n plus 1 minus 1. Okay. So this is induction, which is just like recursion. So you figure out the number of moves by having the number of moves for a simpler problem. Okay. In this case, we are solving a tower with 10 coins by 9 coins. And for 9 coins, we get 2 to the 9 minus 1. Double that, you'll get 2 to the 10 minus 2. But then you add 1 coin. So you get 2 to the 10 minus 1 again. Okay. So this is a lot of moves that you have to have. And so let me go back to the tower here. Okay, so this was our first example of recursion, and in a few minutes I'll turn to the second. Okay, so just as a small digression, as I said, there are many versions of this Tower of Hanoi. It goes all or many dating back from long ago. And what in particular, there is one story, which is that there is a temple in Banaras where you have 3 pegs with a Tower of Hanoi with 64 coins set up. Okay. And the priests there are supposed to keep solving the Tower of Hanoi. And the legend is that when the Tower of Hanoi is solved, then the universe will come to an end. Okay. So there are 3 reasons you don't have to worry about this. One is there probably is no such temple. I've been to Banaras a couple of times. I never heard anyone in Banaras mentioning this. 2, if the problem is solved, that doesn't mean the universe will come to an end. But 3, which is the reason here, we saw how long it takes. It takes about 2 to the power of 64 moves. Okay. Now, the good thumb rule when you want to work with such numbers is 2 to the 10 is 1024, which is about 10 cube, which is about 1000. So you do a quick calculation, you'll see that 2 to the 64 is about 4 into 4 followed by 18 zeros. So if you allow 1 move a second, okay, I just calculated this morning, that takes a little over 10 billion years, by which time the earth would have been swallowed up by the sun anyway. So even if this was true, so the one mathematical aspect of the story is that it's just going to take too long, even if you assume that the priests can keep making a move a second, which is quite not possible. Okay, so anyway, that's part of the story. This was the Tower of Hanoi. Okay, but how about, so solving a random tower on the other hand is not that different from it. So when solving a random tower, there are 2 cases. As I said, either this coin is already in the correct place or it's not. If it is in the correct place, we are just solving one tower, one single one. If it is not in the correct place, then we are solving again two different towers, and then making the additional move of moving it to the correct place. Okay, so this is the same principle we have. Okay, so with this was meant to illustrate this. As I said, you can go and get a physical tower of Hanoi or download an Android or whatever Apple Store game if you happen to have a smartphone or a tablet, and play the Tower of Hanoi on it. Physical one is nice. This is meant for, you can also do it here. This is very crude. This is homemade for this illustration. Okay, so now let me turn from this to different problem. Okay, so which is a more practical one. This was a puzzle which illustrates the same principle. Okay, and that principle is recursion. And this is the practical problem of sorting a bunch of numbers. Okay, something that is done all the time in a computer. Okay, so let me switch to which was it? Control tab. Sorry, I think I'm the wrong screen. Yeah, so here it is. So I'm going to talk about recursion and a way of sorting numbers called quick sort. Okay, I hope this is visible enough, but since this is not interactive, let me see if I can zoom it even. Yeah, let's zoom it a lot so that these things become very visible. Okay, so here we are. It's a quick sort. Okay, so we want to sort the numbers, a list like this. These are all for simplicity integers. Okay, they are lying between anything, doesn't matter. They're all positive integers. And you want to make them from the smallest to the largest. There are many ways of sorting them. Crude ways like picking the smallest, putting it below in the beginning, which is insertion sort. But a very nice algorithm is a recursive one. It's called quick sort. There's another called merge sort, which is also recursive. Idea is we'll pick one random number in the list. Okay, I'll call that the pivot. So for example, here is 132. And then I'll break the list into two parts, those that are below the pivot and the above the pivot. Okay, so here are two lists. Yeah, and then I sort these separately, again using quick sort recursively. So just like we solve for a smaller tower, we sort a smaller list. Okay, so there we are, we get this one and this one. And in between, you put the, so then what is the final answer? We have a sorted list. We put it here all the way up to 119. Put the pivot, because everything here was before the pivot, and put the larger list. And there we are. This is sorted. Okay, so just for illustration, let's just run this here. Okay, this is a language called Scala. I don't want to get into it, but I just want to run things. It is much better for, say, recursion than Python, which is probably the most familiar language to people. So let's call it qsort. For whatever reasons, I'm going to take what is called a vector instead of a list. So I'm doing this. Of course, some of you do know some programming. I mean, but mainly to illustrate that these things are rather easy. So what I want to do is pick a pivot. Okay, so what is first of all pivot? I'll pick value, means just the value of pivot is going to be the vector at some random point. Okay, and I'll vector dot size. So I pick a random pivot. Okay, don't worry too much about that. And then I have two lists. One is before. What I'll do is filter out those elements which are less than pivot. Okay, so value after is vec dot filter those that are greater than the pivot. Okay, and what is the answer? Well, I'll sort those before. And then don't worry too much about the syntax. The next comes the pivot. And then comes the rest of the list, which is quick sorted after. And that's it. So this is all I want to point out. So the method is really very simple. It's very simple to carry out by hand or do it this way. Okay, which is just you throw in the so you sort, break, pick a random thing, call it a pivot, pick those before, pick those after. Let's make a random list here, value example, And I'll make this example having, let's say, 10, or let's have 15 entries or something for this. Uh, and each of which is between 0 and 100. Okay. So here's the example generated. It has 10 entries. Okay. And let's quick sort it. These are in random order. Aha. Curious. Okay. Bound must be. Oh, okay. So I made a silly mistake. This is good. This illustrated nicely what I wanted to do. Of course, this argument is stupid. We have to solve. There is a missing step here. Namely, the missing step is what happens if I have a list with just one element. That's the pivot, and that pivot is going to be of size uh, only element. What if the list is empty? There is no pivot at all. Okay. So if vec dot size is less than 2, vec else this thing. Okay. So by making my mistake, I illustrated the point of recursion. When we solved the one tower, we did not reduce it to solving the 0 tower. We just solved it. Okay, so that is the point. So here, similarly, when we want to make a list with, when we want to sort a list with 0 or 1 element, we sort it. Namely, it's already sorted. Okay, so this one went through, and indeed now it behaves itself and sorts it. Okay, so the principle of recursion here we use in quick sort is we want to sort a list, we break it into sorting simpler lists and such a way that we can put things together. Except in the simplest cases, I have to say what to do. You can't by magic say everything gets simple to infinity. It gets simplest. In the simplest case, which is for an empty list, we got this. And indeed, we got this result. Okay. So let me do the last thing and then I will, if there are any questions, I'll be happy to answer. Let's watch what happens here. We'll just modify this a little bit. Okay. To add the something here. So sorting, let's say, show, well, what do I want to show? I want to show the vec, and let's say pivot. Okay, so let's sort the example here and watch what happens. Okay, so we are sorting the whole thing. We found the pivot 27. And the list before that was 24, 25, 18, 16. And after were these numbers. They're all in random order. I have simply filtered out the list. Okay, so then what do? We sort this one. So we are sorting 24, 25. The pivot was 25. Before was this, and now and after nothing is this. I happen to choose the largest number. Again, here I find a pivot here. So before I got 16 and after I got 24, because these have size just 1, no sorting is needed. That's all happened. Then I got to work sorting the other ones that come after this, and we go here. Okay. So this was an example of a very practical thing. This principle recursion pervades everywhere and is at the center of a lot of practical answers you'll solve. Sorting is indeed one of the practical problems that you face with a computer. And this was a simple recursive solution. The last comment I'll make before from my side before answering any questions, if there are, is that in a modern computer, we actually usually have many cores. Like this one has 12 virtual cores. And a nice thing about this is that this can be parallelized, something like this, as can the Tower of Hanoi. That is, you get one part when you break it into two problems, you tell one core to solve one problem and the other core to solve the other problem. Okay. Indeed, if you imagine you were all in a physical room, you could try to sort lists by making each person, one person just chooses a pivot, breaks it into two, and then passes off to two people that do two lists to sort, who repeat this process. You can organize yourself. With that, I will say stop here. Thank you.
Thank you, sir. Now we would like to ask if any participants have any question, they can text us via chat and we can ask them to sir. So I have a question. A participant has asked, thank you, sir, for the amazing introduction into recursion. I would really appreciate it if you could give a real life example of recursion and how is it implemented in our daily lives.
Uh, so first of all, this is a real life example. Okay. Quicksort is itself a real life example of recursion. Uh, I cannot, I don't even know where to begin. So lots and lots of algorithms in real life. Okay. You want to search for an element in a list. Okay. So for example, a Google search would be different. So you want to search for an element in a list. That's the first thing I can think of. Break the list into two parts, search here, search there. Okay. So actually searching leads to another interesting example where you use recursion in a different way. Let me try to give a elaborate example. Just one moment. Okay, so let me turn to a different recursive. Maybe that's a bit. Yeah. So in okay, so here I've talked about recursive algorithms. Let me turn to a recursive structure. Okay, so here we are. So that recursive structure, if I manage with my misconfigured thing, is what is called a Huffman code. Okay. So at the basis of this is a recursive structure, which is called a binary tree. Okay, so I've talked about recursive code, and so a binary tree is something where I'll draw an example and then I'll try to explain. Okay, so I talked about solving recursive problems, and here is an example of a recursive structure. It's a structure built up from the simpler ones, by certain procedure recursively. So a binary tree is one of two things. It could be just a point, or I take a node like this and put a tree here and put a tree here. Okay, so this may be a tree and this may be a tree. Okay, so what about binary trees? They're used for many problems, but there is a certain problem called a Huffman code. Let me give an example of that. Okay, so I'll give a cartoonish example. Real life examples are actually very similar in nature. Morse code. So you'll all have heard of Morse code. You may not use it. Okay, so I'll say what a more realistic example. Now in the Morse code, you have codes for different letters, but those codes have different lengths. Yeah, so you would want to have a short code for a common letter like E and a large code for a very, it's okay to have a large code for a uncommon letter X. Yeah, so when you want to assign codes to words, you want to assign codes in such a way that you have short codes for the uh, common letters. Now, similarly, you could do this for any kind of encoding. You want to encode words, you want to encode a sentence at a word level, and you use common words having short representations and uncommon words having long ones. This is what would be called lossless compression. Okay, so you don't want to lose any information, but you want to make things shorter. Okay, this already happens in a written language. We tend to have short words for common concepts and long words for uncommon concepts, just so that the things become shorter, the total speech becomes shorter. But what if you want to do it in a systematic and way? Okay, so that an example is the Huffman code, which does exactly this. So what we do is we'll have a code. Suppose we are coding so that we write things in terms of zeros and ones. Then we have some word here which is common, like the, and here slightly less common words like so and it maybe, and maybe a rare word like rare will come further down. You see, the will have just a 2-letter code. These will have 3-letter codes. And on the other hand, I'm going to have, so maybe I want another common word here, which is a 2-letter word, and or something like that. On the other hand, the word rare will have a code which is 1110. So rare is going to be 1100, which is going to be 4 letters, while D is going to be just 00, which is 2 letters. Okay. So this is a recursive structure where you put words together. Okay. And based on how they are sitting in the tree, you get a code in zeros and ones for this. And so that the common words are going to be on top and the uncommon words below. So this is something that is used practically heavily. It's the Huffman Code from 1954 or something like that. You could think of it yeah, you could think of it in terms of like telephone numbers. These days, we all have the same size. Okay. And so how do you find the Huffman code? So there is a recursive way. You take the two most uncommon words and club them together. And then here you put total weight. Okay. And from then on, you treat them as the same word. And so if it is still one of the most uncommon, it gets clubbed with something else. But once you club these two, it may become more common than two other words. So then you club those two together. Okay, I just sketched this very briefly, but the idea is really quite simple. You club the most common ones and then you treat that as one unit, with the weight being the total weight. Okay, so common, so the weight meaning the frequency with which a word occurs. Okay, so you frequency of either of them occurring is on top of a tree. And then you take the two most uncommon nodes here. So it may be word or collection of words, and club them together. And you repeat this. And this actually gives you the best way of compression. So that is another example in real life. Yeah. Okay, thanks.
Thank you, sir. We have another question from Himansh Ahuja, and he would like to know that which type of code this is, which we were currently seeing on the screen.
Which type of code? Let me pop it up on the screen and show you. This is a language called Scala, uh, quite widespread. And this is what is called a Jupyter Notebook running. And so I'm using Scala because Python, for example, which is probably the language most people know here, doesn't support recursion very well. So if you're used to Python, Python does allow recursion. Okay, so you could write the same code in Python if you know that, or in basically any modern language. So ancient ones like Fortran literally don't allow recursion, but any modern language does allow recursion, but some of them don't support it very well. So it can cause the thing to crash for fairly long lists. A language like what are called functional languages are designed to have recursion as the main send mode of flow of control, and so they will be so I use that, which also I'm just more used to it. So that's yeah. So this code, so that's why you'll see in some other languages you don't need this val stands for value, otherwise it's not that different. Yeah, also I have to slightly uglier pictures. I made these lists look like Python lists, that's why I had that show from earlier. Okay, but you'll see this kind of printout is a little less nice syntax. But yeah, so it's a language called Scala, and this is a what is called Jupyter Notebook. It's an interface where things can run on the web. So this is running in a browser. Yeah. Okay, thanks.